Good morning, everyone, and welcome to the 25th ETP4HPC webinar. I am Pascal. I'm ETP4HPC's Communication Manager. And for those of you who are not familiar with ETP4HPC, we are a non-profit association that promotes European research and innovation in HPC, and we are a private member of the EuroHPC JU. And I've lost my slides, sorry. So a couple of practical information because we get into today's topic. This webinar is recorded. You will receive the link to the recording tomorrow. The webinar is in listen-only mode, but you can use the GoToWebinar control panel, that's illustrated here, to ask questions or to download handouts. And today we have the slides of the webinar as a handout, so you can download them right away. You can submit questions at any time during the presentations. I will share them in the chat so everybody can see them, but we'll handle all questions at the end of the webinar after the two presentations. So I would like to introduce today's speakers. So today's webinar is a little bit special because it's kind of a replay of a live session we held at the EuroHPC Summit back in March. We had put together a session on emerging technologies for European HPC, and it was much appreciated. So but it was not recorded, unfortunately. So to share it with as many people as possible, we have invited again the speakers we had at this live session, and we're organizing two webinars based on the same content and with the same presenter pairs. So today we are very happy to welcome again Tobias Becker from Maxeler Technologies and Robert Haas from IBM Research to talk about unconventional HPC architectures. And after Tobias and Robert, we'll have Craig and Marc. Craig Prunty is from SiPearl and Marc Duranton from CA. So, yeah, quick look at the agenda. And I think we are ready to start. So, Robert, are you ready to share your slides? I will hand over to you.
Yes, please.
Now you should be able to share your slides.
Okay, can you confirm you see?
Yes, I can see your slides and they are in slideshow mode.
Very good, excellent. So Tobias, you kick it off.
Okay, thanks for the introduction. So in this presentation, I would like to talk about unconventional HPC, looking at it from the architectural and component level. So if you go to the next slide. So we really see an emergence of unconventional architectures in HPC. And so the question is, how do we get here? I mean, we're all familiar with Moore's law, and we've seen a remarkable trend in our industry driven by this exponential scaling of this fundamental building block of the transistor. We went from a few dozens to now more than billion transistors being integrated. But we've faced some challenges along the way. I mean, 15 years ago, the clock scaling ran out of steam, so that forced a shift towards more parallel architectures and multi-core. And more recently, Moore's law itself and the scaling of the transistor itself is running out of steam. It's slowing down. It's becoming increasingly expensive to keep up doing this. At the same time, we still have this increasing demand for more performance in both HPC and AI. So simply, more parallelism is not enough to fill the gap here. So what happens is that we see specialization is spearheading further gains in both performance and efficiency. So there's a couple of noteworthy trends that we want to cover in this presentation. First of all, we see emerging specialized architectures and accelerators that are being used as novel components in HPC. We also see increasingly non-von Neumann and non-CMOS options becoming available. There is increased interest in alternative models of compute. So, for example, increased locality of data through both data flow or processing and memory. And then we also have unconventional models of compute and, for example, unconventional arithmetic. But the challenge here is that as these being introduced, we need to look at the programmability of these architectures and software development, software maintenance as you know, software is being ported over to these architectures. So the first one that's noteworthy is FPGA accelerators. An FPGA is essentially a programmable and configurable fabric. So you can fully customize and build your own architecture on these chips. Therefore, essentially you get highly parallel and low clock frequency implementations. And because of this property, you end up getting high performance and both high power efficiency as well. So that's very attractive in this field. They're being used in a range of different applications. Maybe noteworthy is finance has been driving demand for both performance and latency, but also in a lot of different HPC-related applications, for example, seismic, fluid dynamics, and so on. So there's a lot of interest in using them. But there is the key question here for FPGAs is programmability. There are, of course, different frameworks, like, for example, high-level synthesis, OpenCL, the Maxeler tools. But fundamentally, the programmability challenge is something that's holding FPGAs back a little bit before becoming more mainstream in this field.
So Tobias, I mean, we know FPGAs now for a long time, right? So why now? Why should we consider these as unconventional in the field of HPC in particular?
Yeah, I would say two reasons. I mean, FPGAs have been around for a long time, but mostly in other fields like logic emulation and maybe mobile base stations, telecommunications, and so on. So they haven't really made a big splash in the HPC field yet. And I would say they're unconventional because it's not a programmable instruction set architecture. It's essentially a flexible fabric where you build your own circuit. So you don't have any cores that you program, you build your own core, so to speak. But that also leads to the programmability challenge.
Very good.
So the next one that we should maybe cover a little bit here is AI accelerators. So we now see novel accelerators in the field of AI, and they're really driven by novel AI applications, really anything from image classification, self-driving to large language models, which is the latest field that gets a lot of interest. And examples of such architectures are, for example, the Google GPU, which was one of the first ones to become available, GraphCore, Cerebras, or Grok. And so broadly speaking, I mean, they all have their own characteristics, but broadly speaking, they're matrix-oriented. They include some form of massive scale parallelism. And in the case of Grok, we also have a data flow model, which we previously used in FPGAs as well. All of these AI accelerators, they're typically used or programmed in the context of novel and emerging frameworks. We have TensorFlow and PyTorch are very popular ones. JAX seems to be emerging and covering both HPC and AI. So there is a lot of development here, and there is potentially a lot of potential for using them in converged HPC and AI applications as well.
Indeed, Tobias. So same question as earlier for the FPGA accelerators. We see this advent of the field of machine learning and AI, which is leading to this wealth of AI accelerators. So how relevant can they be for HPC?
That's a really good question. So we can, the low-hanging fruit would just to use them as an accelerator for the same algorithm. But what's maybe more interesting is this example of converged compute. You see an example here with a CFD. And so instead of just accelerating the traditional algorithm, I can, for example, convert the algorithm into a pure AI algorithm where essentially, instead of me programming the algorithm, some sort of AI can learn the equations and then perform the compute that way. Or I can have this so-called converged model where it's some sort of hybrid of a conventional algorithm plus an AI step that, for example, in this case, performs upscaling, downscaling, and delivers a much more efficient computation of the same model, and essentially results in sort of a hybrid where this accelerator, this technology would work really well.
Very good. Let's move on. So data flow.
So data flow is something that we've already mentioned in the context of FPGAs and some of these AI chips. So why do we consider data flow as a computational model? So it really addresses some of the fundamental limitations that we have with our current technology, that is the memory wall. So we're all familiar that going off chip is increasingly expensive in terms of both latency and throughput and also energy. But even on chip, moving from the processor core to various stages of, for example, cache, brings a lot of penalties in terms of the time that it takes, but also the energy. So the end game really here is that data moving is becoming one of the key considerations for efficient compute. And data flow addresses this at this core. So instead of me operating on data in memory, I now move data through operators. And that is naturally very parallel, it's very efficient, and it increases the data locality. So where's this naturally very suitable? Well, obviously in networking applications, because that has a data flow characteristic, but also in FPGAs and AI. If you look at data flow, static data flow in particular, it's a really good abstraction also for hardware-oriented compiler optimizations. So the model of compute is very deterministic, or it's deterministic in its low latency, and that means I can push a lot of optimizations into the compiler because the compiler will know what's going to happen. And it leads to very scalable implementations because fundamentally everything will keep moving at sort of a known rate at runtime without anything stalling.
So let's move on to mixed precision.
So mixed precision is a field that gains a lot of attention recently. And it's essentially, we're moving away from the standard double and single precision floating point arithmetic that are common in HPC. Why do we do this? Simply because a lower precision model can be much more efficient in terms of both performance, but also energy that is needed to carry out the compute. You see an example here of a seismic computation being transformed from single precision to a fixed point. But the key question is how much resolution do I really need? And that can be a difficult question to answer. So all of this needs to be supported with frameworks to analyze applications to find out what the right number formats are. But we do see a lot of interest in lower precision compute in the context of FPGA architectures, but also now through AI. So we see that in AI and AI optimized GPUs as well. So come to think of this, our brain is a very good example of essentially sort of a mixed precision compute engine. I can calculate something very accurately, but I can also do something like facial recognition, which doesn't really require me to have a high fidelity model of the person that I recognize. So is there something from this brain model that we can abstract and apply to computing?
Indeed. So let's go and look at this a bit more closely. And clearly, the advances in neurosciences dating back from last century already are constantly helping us refine the models of how we believe our own brains are working. So there's a whole field around that called neuromorphic computing, broadly speaking, right? Which can be defined as following, right? Exploiting characteristics that may also occur in terms of how our own brains are functioning, in terms of information encoded in time, sparsity of representation of information, although there is always new discoveries that indicate that our own brain may not be completely sparse, but sort of a pseudo-sparse, which makes it work better also with very noisy environments. We can also consider the use of physical phenomena to carry computations, and we'll come to that in a moment with real examples that have been demonstrated already, as well as new materials, or sometimes old materials that we are repurposing in a way to store or simultaneously store and compute. As we know, our brain essentially mixes these things as well. Now, when we talk broadly about neuromorphic computing, I mean, one example that really comes up very often is that of spiking neural networks. I wanted to spend a little moment on this and describe here how things have evolved over the recent years and how actually we've seen a possibility to merge or converge the work that took place on the spiking side with the work that took place on the artificial neural networks side. And let me explain that a little bit better here with this following figure. I mean, if you go all the way back to 1906, right, where the black reaction method was refined by Ramon y Cajal back then, and that led to a Nobel Prize and the discovery that our own brain was not composed of a single cell, but actually a multitude of neurons interconnected with each other at synapses and the like. From that point on, we can broadly say there were two trends, right? The first one, the top one, essentially was more looking into the simulation of the structure of the brain, and that led to artificial neural networks, right? And they've been so successful, as we know, over the decades, but it took quite some time for this to pick up, and there were like critical steps along the way that popularized some technologies such as backpropagation and sequence capability with LSTMs and the like, which made, I mean, artificial neural network and the acceleration thereof use GPU something that can address so many problems. At the same time, in parallel, you see on the lower half of this page, there was another thread of work that was more about the emulation of the dynamics side of neurons, right? Starting with models of spiking neural net dynamics. You saw that back in the 50s already, but then also work towards neuromorphic engineering by Carver-Mead that was essentially using VLSI technology to mimic the neuron biological architectures, followed by the spike timing dependent plasticity, or STDP, by Markram and others, really, that stated that when neurons fire together, then they will wire together. So there's a causal link that gets reinforced by increasing the wiring of such connections of neurons. And then, I mean, in the last decade or so, also a wealth of different neuromorphic accelerators out there, and obviously the SRA document will go and list many of these examples here. So here's what we have seen, what we have witnessed, and let me now show the next step, which is essentially bringing back these two threads closer together, or this convergence of SNNs, right? The emulation of the dynamics with the ANNs, essentially the structure of such networks. And you see a good example, well, one example here at the top, where you see a typical recurrent neural network with a unit based on LSTM on the left-hand side, which requires a large number of parameters, therefore effort needed to train them appropriately to reach the necessary accuracy. And the internals of this cell are relatively complex, right? That essentially takes time, that takes effort until you can train these networks appropriately. Now comes the right-hand side, where we are essentially mimicking a typical leaky, integrate, and fire behavior of neurons, from what we understand of neuroscience more and more, right? This requires fewer parameters. It takes advantage of different neural dynamics that are not found on the LSTM side. And it can be extended further as we learn more from neuroscience. If you want to really go and benchmark the two, and that's what's done, actually, I just show some results. You see, because of the complexity difference, the number of multiplication, the inference time, and in the end also there's a line about the accuracy. I mean, there's quite some benefit going towards more neuromorphic, brain-inspired approaches, such as the one that is shown here with this spiking neural network, while taking advantage of all what has been built so far in artificial neural networks, namely all the backpropagation algorithms and the like that made it so popular.
So I have a question here. So previously we talked about the concept of data flow computing and how that's applied to FPGAs and AI chips. There's a similar concept under the name of processing in memory. Can you say a little bit about that?
Indeed, PIM, or processing in memory, is actually can refer to a number of things. So let's look at this in a broad way. It's essentially integration of computation with memory arrays, with peripheral circuits, into logic layers and dies that are integrated into the memory devices, right? That's how we often look at this. And it also extends to concepts such as analog computing and as well photonic computing. But let me now say a few more words about the in-memory computing, which is really taking a more drastic step in the direction of processing in memory, which means in-memory computing, as you see illustrated at the top right, takes a different approach from essentially shipping data back and forth between your processing units and your conventional memory to shipping functions into the memory, which then becomes a computational memory, so that there is much less traffic going on between the processing and the memory itself. This can be realized actually with a number of technologies. Many of them have been demonstrated so far, right? It can be, as shown below, charge-based, resistance-based memories. They can be volatile, they can be non-volatile. All this exists. What this actually enables us to do, and this is shown on the left-hand side, is quite interesting, is to break through this wall in terms of peak performance, operations per second, or operations per watt that one can go and achieve from the conventional paradigms, which is shown at the top right, to this in-memory paradigm, which is what I'm just describing here. And the idea here, and there are already some results out there, I will come to that in a moment, showing that we can break through this 10 teraops per watt barrier, which is essentially the diagonal going through the graph on the left-hand side, and could imagine reaching performances in the range of 100 teraops per watt or more. And that would be substantial in terms of like enabling new applications and really achieving some of the sustainability targets that we all strive to do. Now, let me show you a concrete example as an illustration of the work that indicates that there is potential for that. So there was recently a demonstration of a 64-core fully integrated, so mixed analog and digital signal processing on a chip, CMOS chip with back-end of the line integration of phase change memory. That is essentially the non-volatile memory component that is used for computational purposes. This is 14 nanometer CMOS technology, and the results are staggering, right? Reaching close to 10 teraops per watt, which is substantial if you compare that to conventional accelerators today, and also achieves substantial benefit in terms of the density of capability, of computational capability of matrix vector multiplication throughput per chip area, which is at least 15 times more than any other resistive memory-based analog in-memory computing chips that have been shown so far, with at the same time achieving the highest accuracy on benchmarks that are used to compare this. And this shows us what I was referring to earlier. There is potential to go, and you see this at the top right, from a structure where we spend 300 femtojoule per operation, because we are moving data back and forth between the processing and the memory, trying to achieve a possibly 1 femtojoule per operation target at some point in time using this in-memory computing cores.
So, Robert, we've talked about computing so far. Is there anything noteworthy in the area of storage that may classify as unconventional?
And clearly, yes, Tobias, because I mean, especially now, given the advent of generative AI and the masses of data, of models that are being created, all of this is very expensive work that has to be conducted on various types of infrastructure. One needs to go and start to collect all this information and keep it for various reasons at the lowest possible costs. And I like to say one kind of storage technologies that used to be very conventional to the point that it was almost promised to disappear at some point in time has gone through a major renaissance, if I may say. And this is magnetic tape storage based technology. The reason why it is interesting is there is now again and again technology demos that are showing, and these are shown with the blue lozenges in the middle of the graph there, technology demos demonstrating an increase, a constant increase, but this is a logarithmic scale, so it's a exponential increase in areal density that can be achieved for the years to come, and predict essentially what can be delivered in products in the next 10 years, whereas other magnetic storage technologies, namely HDDs, have plateaued in terms of their growth in density. And that's important, I mean, to have these technologies available, because at some point in time, we will have petabytes or exabytes of data to put somewhere. And if you can store versus 30 cartridges today, but put all of that on a single cartridge of more than half a petabyte, that is going to lead to substantial savings, cost efficiency, obviously, but also sustainability-wise. All right, so we're coming close to the end of the first part here. Now, as we integrate more and more of specialized computing capabilities, such as the one that we briefly covered, Tobias and I, so that HPC can also tackle AI, what kind of challenges will this lead us to?
Well, I think the first observation here is that specialization is certainly here, right? So we've seen the emergence of several new accelerators that are essentially customized to a certain sort of model or area, and delivering the additional performance gains that we wouldn't necessarily get with a traditional off-the-shelf CPU architectures. We talked about AI accelerators and FPGAs, but also neuromorphic and CMOS. And as we discussed, they come with their own models and new trends as well. So it's not just a like-for-like replacement. So for example, we've talked about the convergence of HPC and AI, which leads to transformations in the algorithm, or can lead to transformation in the algorithm to unlock the full potential. We've talked a little bit about the kind of the lower precision modes of computation that can gain further efficiencies. But all of these require some special attention. They're not as easy to use as, let's say, earlier trends of multi-core, going from single core to multi-core, which was a more sort of a conventional model that was easier to use. So essentially what this all leads to is, we have co-design and programming challenges to use all of this efficiently. And I think what we really need is we need new approaches for this. Ideally, they should be open and ideally non-kernel based. So I think just pushing this to a vendor to just come up with a sort of libraries that people then use isn't very scalable either. And these approaches need to be also scalable on the architectural level to allow us to build small systems, large systems, and using all heterogeneous resources efficiently.
Excellent. Thank you.
Thank you, Robert and Tobias. This was really good. I enjoyed your presentation. It was the second time I saw it, but last time was live in Göteborg, and I was busy taking pictures and tweeting about what you were saying. So this time I was really able to enjoy it. So thank you. We already have some questions, but we will answer them at the end. So now I will ask Craig and Marc to get ready. Craig, are you ready to share your slides?
Sure. You have to give me authority, right?
Yeah.
Show my screen. Which screen is showing?
Not your, well, we can see your slide very small in the middle.
Okay, so wrong screen. So I don't know how
it's your background, I think.
It didn't give me a choice on sharing which screen.
Can you maybe try and go to slideshow mode?
Voila, different screen. I figured it out. Is that
Yep.
better?
Yep.
Okay.
That's perfect.
Okay, so we'll jump in.
You can go ahead. Thank
Okay.
you, Marc and Craig.
So we want to cover a bit more on the system, subsystem, and interposer level. So really the things that sit in package. So following up on the presentation you just saw, talking about how you see variation in the system level and solutions, we want to take that and move it a step down into what we see actually happening in chip today. So this presentation was put together by Marc Duranton, by myself, and also a third person, Denis Dutoit, part of CEA. I wanted to mention because a lot of these slides really were generated by him, even if he's not presenting today. So first, just as an introduction, we see the system hardware components, and this really follows up on what you heard in the presentation before. You see new types of acceleration, new kinds of software, security in chips, a lot of new needs in terms of the processor, and in terms of acceleration elements, we're seeing more and more brought into to systems and processors today. So we're seeing a combination of a possible disaggregation at the system level, but more and more aggregation at the component level. And in terms of the component elements, specifically, we see obviously CPUs and different kind of CPUs now, specifically talking about server processor architectures, with RISC-V being not viable today, but interesting for the future from an ecosystem perspective for a CPU server processor. GPUs, DPUs, or IPUs, what we see as accelerators traditionally on NIC cards today. Also TPUs, FPGA, so specific kinds of acceleration, and then variable precision, other kinds of acceleration on the market, like AI. The TPUs is an example of that. We also see trends in memory and near processing storage, as was talked about in the previous generation. And then to bring all this together, we need short distance interconnect and 3D types of interconnect that can allow these to efficiently work together, even coherent interconnect. This is all based on the work that we did in the SRA5, the Strategic Research Agenda, the 5th generation from the ETP4HPC. So you can find that available now publicly and specifically on these system hardware components from page 84. In terms of other kinds of integration, so we'll talk about memory, the different kind of packaging functions we see, and again, functional disaggregation, but integration within package, and then some trends on open source hardware.
So let's try to explain what was the drive between for this evolution of the architecture. So in the gold all the time, so the technology was good for the architecture. So each time you go to a next technology node, you could double the frequency. So that was the monocore architecture. So that was until 2006, where basically the physics was not so nice. And when you have more increase in density, then you cannot reduce the power and you cannot increase the frequency, but still you have more slow that's allowed to have more transistors. So the logical drive was to go into parallelism, so a multi-core then many core. But as also the power density now is increasing, we hurt now the power wall, and how to be more efficient is going to more specialization. So it's why we have now heterogeneous architecture with various accelerator for various application. But as we need to go more further into performances, so we cannot increase further the size of the number of silicon per of transistor per area. So we go into a new approach that link to the chiplet and interposer. So basically, this also drive to have some new organization, new architecture into the system, and now all the major high-performance processor like AMD and Intel are using this chiplet-based architecture that really allow this disaggregation of at the global architecture level and the reaggregation at the chiplet level. But let's see a little bit more what is this idea of a chiplet on interposer. So, so the idea is, instead of having a big monolithic silicon, you cut it into a more smaller pieces that have a lot of advantage. For first, the yield. So if you have a smaller chip, then it will be more unlikely that there is a default in it. And the second point is that each chiplet could use a technology which is more suited to its functionality. So the technology for computation is not exactly the same technology for SRAM, not the same for analog, which is needed for power converter, for example, or for non-volatile memory. And all these small chips are put not into a PCB like we have now, but in an interposer, which is at the package level, a kind of a smaller PCB, printed circuit board, that's allowed to interconnect all these chiplets. And the interposer could be also active, meaning that as it's based on silicon, you could have a transistor that could make functionalities like routing or for power consumption. So you could see on the right of the picture an example of this chiplet on an active interposer. So you see the dimensions are very small in the size of hundreds of micrometer for the connection between the chiplet on the interposer. So that's allowed to have a very dense and very powerful architecture, hundreds of GOPS in a very small area.
So if we take what Marc just described to sort of the extreme from a use case perspective, we can then have this Lego block solution where we have a physical and logical interposer layer, and this could be our CPU and orchestrator, and then we can have a number of different accelerators sitting on top. Now, I won't go and build this solution. This is kind of a Frankenstein with all these different kind of accelerators in one design, but it shows you what's possible. I could have multiple neuro engines and potentially GPUs as well in the same solution. And this allows me to start composing architectures that are, the architecture is focused on the workload instead of the workload adapted to the architecture. And this is the trend we're seeing more and more with different kinds of acceleration in system. Each of these accelerators is very efficient for the workloads that it's designed for, and it tends to be inefficient for many other workloads. So by adding different kinds of accelerators in a system, I'm able to support different kinds of workloads in that system very efficiently, both in terms of power and performance. Again, this is not something that we see today from multiple companies. There are a lot of things that have to be solved before this becomes a sort of a Lego block solution. It's not just a question of getting the right interface. You also need to have your testing flows. You need to have your in-band communication. You need to be able to sit this in a package with the right power and connectivity up through the package. If you're going to do 3D stacking, you have to be able to manage the power and the cooling through this. There's a lot of things that have to be standardized before this becomes a true Lego building block. But we can see the path to that. And again, today you see it in single companies where you have these 3D architectures with active interposer. And if we look at the right, to the right, we see different kinds of technologies that have implementations in silicon. So you can imagine that these technologies in silicon then could be brought into, in the future, a packaged option in a chiplet format. So for instance, neuromorphic, there are certain technologies in quantum that sit on silicon. There are others that don't, and they wouldn't sit in package, but they would be closely orchestrated. And then obviously silicon photonics is an area of a lot of interest, whether it's an optical interposer or whether it's connecting photonics for disaggregation of systems, either close or a bit further away.
So one advantage of having all this unit under the same package is that it's reduce the communication length between all the units. So Craig, if you could go to the next slide.
Yep.
Yeah. And here we will complement what Robert said about computing in memory or near memory. Even if you are using conventional system, the cost of communication is very high. So for example, if you have a compute operation that basically take 20 picojoule, if you want to compare and to bring the same data to this from DRAM, so that takes basically a 3 order of magnitude more energy to bring this data to the compute part. So really, the key point is to reduce this data movement with all this idea of compute in or near a memory. And what is very important is that thanks to the chiplet on interposer, by nature, the length of wires is greatly reduced. But it's also allowed to have new architecture using sharing memory, where processor and accelerator could share the same memory and not having the ping pong between processor going to memory and then memory going to accelerator. So this optimization of memory structure is really helped by the idea of having all the different systems on this chiplet plus interposer approach. So typically, if we go to the next slide, this is the evolution that we see. So Craig, perhaps you could discuss more about this evolution between this chip level and system level of the.
So first thing I want to talk about is when we say system level here, we're talking about system in package. So we're not talking about system in terms of server. We're talking about system in terms of chiplet architectures in package. So the focus here is to talk about what kind of gains we can see in terms of moving from a pure single die in package to multiple die in package. So we can get to roughly 50 billion transistors in a package, and that gives us a lot of compute. But if we move to a system level chiplet architecture, it distributes a bit the compute, allows you ultimately a bigger package, and then allows you different ways of cooling that solution with a bigger package as well. So we can scale up at least 6x in terms of the number of raw transistors. That's one piece. The thing that we see with Moore's law is that the transistors are still scaling even today, but the interconnect is scaling less and less with lower geometries. But with the advanced packaging, then we can actually use 3D to also scale our interconnect. And that's one of the big challenges, is if I add more compute, I still have to bring data to that compute, and I still have to be able to communicate between the compute elements. So this dense high D for communication throughput also gives us the density of the interconnect to match the density of compute.
So this allows basically to have a total rethinking of the architecture of the compute system. So that will lead to a disaggregation of the actual architecture, where you have basically a blade of CPU, blade of accelerator, blade of SSD or of memory. So now we could make this aggregation of all the key elements together under the same package. So here we see that we go from a system that are multiple boards to the multi-chip integrated into this package. And you see that you have a large variety of technology depending of what you want to do. So going from the system in package, which is basically a micro-miniaturized version of a board, a PCB on a chip, to more 3D integration with a chip on top of chip, so using TSV, so through silicon vias, so that's allowed to have connectivity between various layers of silicon, hybrid bonding, so that's allowed to glue together a wafer to other wafer. So you have plenty of technologies that are now developed that allow to basically have a little bit more choice in how you will integrate, not only side by side, so in 2D, but also in 3D by making layer on layer of chips. So of course, the basic technology interposer on chiplet is 3D, because you have a first, the interposer is a chip, and you have the chiplet that are on top of it, but you could make several layers and several technology going on this. And so this is for the functional block, but also in terms of interconnect, as Craig said, this is very important. So Craig, could you tell us more about what is going on into the interconnect in this new chiplet on interposer approach?
Sure. So obviously you have to interconnect the different functions. And again, we break this down. We're trying to aggregate in package more functions and more capability with taking the structural partitioning and the functional partitioning. But to do this, then we have to connect between elements. Now, traditionally, we're connecting on the let's say package to package level at the node level. But within the chip, then we see some standardized and standardized solutions in terms of the SerDes themselves. And if you scale, you see a bunch of wires today from OCP, ODSA. UCIe is now a standard coming with a lot of support behind it. And then you have different high-speed SerDes options that you can take from IP providers. Again, standardized SerDes, but not necessarily a standardized interface solution today. What we see is UCIe seems to be taking the lead, the Universal Chiplet Interconnect Express. And then this will have to link with the socket to socket or socket to interconnect or socket to memory interfaces. CXL offers a real promise here in that it can be a universal interconnect to memory, to other compute elements, whether it's between CPUs or CPUs to accelerators, and to I/O. Today, not all of those are fully, let's say, baked, but those are the three targets for CXL. As a chip maker, this offers a lot of advantage because you would see one interface. So one of the challenges we have as chip makers is what we call beachfront, the edge area of the silicon, and optimizing that. And having one interface that could optionally connect to different kinds of the high speed, all the high speed interfaces could be, let's say, integrated into a single kind of interface would give us a lot of flexibility in how we design chips. So that's the promise of CXL today. And then if we integrate that with silicon photonics, as we talked about before, this would allow disaggregation at the system level efficiently. So taking that these concepts we've had in these slides about functional versus structural partitioning and aggregation in the package, there's really three ingredients we see for the co-optimization. So we talked about the architectural partitioning. With advanced package, now we can have the structural disaggregation, but still aggregation in package. And to do that, we need these die-to-die interfaces. And with the die-to-die interfaces, if we can standardize those along with the different packaging technologies, test technologies, etc., then we can come to a full chiplet marketplace. And with these different kinds of solutions that Marc will talk a little bit about.
Yeah, it's what we are going now, and what is start to emerge, but still missing is this chiplet ecosystem that's allowed to use chiplet from various providers and integrate them, and that also could create a new kind of added value in the chain. So you will have chiplet provider, and then you will have chiplet integrator on an interposer. So that could be a different job. So and then you have the system integrator that use this package using chiplet on interposer. So then we will have one new level that's allowed to have a new architecture developed for this. And typically this is already emerging with what Intel, AMD is doing. Also Apple, the performance of the Apple M1 on M2 are not because they are using ARM silicon, but because they have this approach that's allowed to have shared memory. So between accelerator on the processor, and also having memory near the die, and they could also couple two processor or two dies to double the performance of the system. We could go even one level further, not for HPC, but for embedded system, where we could have sensor on top of a sea of processor. So that could trigger a new range of architecture that were not possible with the discrete approach that we have before. But indeed, what is very important is the communication between all these die. And in the future, it's likely that we could use photonics for the communication. So if you could go to the next slide. So what we have today, so photonics is going up to the blade, but it's very easy when you have a silicon interposer to change the electrical interface by a photonic interface. So that we could see here. So if you could press the button, Craig. Yeah, so you change the interposer, and then we could have photons going from the PCB to the package. But we can even go one step further, and this is what we show into this slide, is that the interposer could also use photonics. So if you go to the illustration, so now we could use photons to exchange data between all the chiplets. So that could lead to a quite complex package where you have a substrate that is a connection to the PCB, the photonic interposer, and then you will have all the components with a very high bandwidth between them. So that could be a new architecture which has very high bandwidth between elements. So basically we see these trends going on. So perhaps Craig, you could illustrate this, yes, into the next slide here.
So this is wrapping up a lot of the things that we talked about. The slide that Marc showed earlier, talking about the evolution of processor architectures from single core to multi-core. We're seeing that here in terms of products themselves. So you used to see different functional elements in a single chip on if we see it here with the Intel Itanium around 2005, and then we started to see integration of vector processing units inside the silicon. And then now we're seeing this moving even further with a more advanced acceleration and even dual chiplet configurations to what we see in the Intel Ponte Vecchio with many, many chiplets in an architecture. And as we go forward, then we expect this moving to marketplaces of chiplets with standardized solutions that people can drop their chiplets into, and many companies working together. So example of Intel here is a blow up with the Ponte Vecchio, and then obviously AMD is doing multi-chip architectures for both CPU and GPU solutions today, and these are available on the market in production. So this is real for single companies today. So in conclusion, we want to sort of sum up the limiting the length of data transfers. I think actually, Marc, I'm sorry, I'm stepping on your discussion points. Yeah.
We could change, no problem. So yeah. Please go on.
Yeah. Okay, so we talk about the different memory in the system and unifying the access of memory between processor and accelerator. So looking at coherent kinds of interfaces across chiplets, looking at faster interconnect, so photonic interposers, for instance, giving us higher bandwidth within the chip, and also extending the size of the package efficiently, and then the programming models that work across CPU and accelerators will be very important, so that from a software perspective, this gets easier and easier. And this is where bringing chiplets into a package is important. The closer that we can get those elements together, the lower the latency and the better the coherency and shared memory models allows that programming environment to be easier. And for accelerators, software is often the blocking point, or let's say the bottleneck in terms of usability.
Yeah, and this also allows to have more fine-tuned memory hierarchy, so better memory hierarchy, really using the best characteristic of all the technology. So, for example, HBM, which has low latency, high bandwidth, a DRAM, which has low latency, middle-sized capacity, and a non-volatile memory, which has a persistency. So we could really have a more flexible at the chiplet and interposer approach. And this is very important also for the new kind of computation, like the one that we have for artificial intelligence. And of course, the point is that if we have this memory, a more optimized memory hierarchy, the software need to take account of this. So the placement of data will be a major challenge to take the best of this new architecture.
Yeah, so, and again, data movement is getting to be a higher and higher cost in both chips and systems. We have more and more data, so moving processing close to memory, either moving memory close to processing or moving processing close to memory, is a way to limit the amount of data transfer. Also sharing memory. We're getting close to the end, Pascal, I see. Also sharing memory between compute elements is going to be very important.
So yes, and we need to have, of course, improved compute elements, so more efficient accelerator. So the previous presentation saw what front could be done, and they need to be as close as possible to the main controller, to the orchestrator of all these tasks that will be offloaded to accelerator. And of course, all these accelerators need to support the most efficient data type, so the best precision. We know that in artificial intelligence, so that tries to the appearance of new coding, like spiking, so where coding is done in time, but also of float 8, which is very new compared to the high accuracy that we are used in HPC. So this is allowing to have accelerator which was more efficient on all these topics.
Okay, so that's the end of our presentation. There's some more reading areas here, especially the SRA5. Please take a look at this. There's a lot of people in Europe in the HPC ecosystem who worked on this, looking at new technologies. We strongly recommend you give it a read. Thank you,
I've put the link in the chat, the link to the SRA.
Thank you, Pascal.
So we are running a little bit late, but we're still here. First of all, thanks very much to Craig and Marc. I hope the audience enjoyed this as much as I did. And so we are running a bit late, but we still have time to take some questions. And sorry, I'm not on the right. Why am I not on the right slide? Yeah, okay. So if you have questions, please use the question, sorry, the questions panel in GoToWebinar. So we have already a few questions. So there was the first one, what about the software library for simulating neuromorphic computing? This was a question from Pierrick Pochelu, and Robert was able to share a link. It's in the chat. All of this is in the chat. You can all see it. So Robert, Tobias, was there anything you wanted to add about this? About software library for simulating neuromorphic computing?
Of course, I mean, this is an open source activity where we are involved with IBM and welcoming anyone else to go and participate. So take a look at it and help make it better, suit your particular needs for the benefits of the community. Take a look at this, and you have more questions, you can always come back to the community there or me in particular.
Thank you, Robert. Then we had a question, what about quantum computing? So first of all, I would like to say that we will address quantum computing next week, because today is part 1 of the webinar about emerging technologies, but we have a lot of material. So there will be a second webinar next week about managing heterogeneity and quantum computing. Now, this being said, and I put the link to register to the second webinar, it's in the chat. Now, this being said, if Robert or Tobias wants to add anything about this, no, nothing to add about quantum computing.
It's such a hot topic these days. I mean, I think everybody sees the latest announcements that are made in the industry. I mean, you may have seen a cover in Nature just last week with amazing breakthrough towards demonstrating the utility of quantum computing. Remember, in the past, we called it quantum supremacy. We changed the wording to quantum advantage. Now we have chosen to use quantum utility as how to refer to this. And I think, I mean, one of the announcements and the paper that was jointly done with University of Berkeley and the team at IBM Research showed that one does not need to wait for hundreds of thousands of qubits in order to get to that level of utility by doing some smart error mitigation on the fewer qubits that you may have available. So take a look at this. This is getting really real.
Okay.
And maybe just a related thought here is that there is a topic which is somewhat different but related in that there's also quantum inspired algorithms. So that is not actually using a quantum computer but using a quantum formulation to solve problems. Like Cubo is an example where you take a combinatorial problem and dress it up as a quantum formulation, and then you use kind of various algorithms to solve that. And in some cases, that even people have built customized architectures to solve these. I think the Fujitsu digital annealer is one example where, you know, this machine was specifically built to solve quantum-inspired problems. We didn't cover this in the first presentation because it's a little bit niche, but that's quite interesting as well.
Okay, thank you, Tobias. Then we have a question from Sabri Plana. From the programming point of view, will interposers and chiplets pose specific challenges? So this is more for Marc and Craig.
So I could start answering. As you see, this chiplet is allowing, let's say, a new era for architects. So they could try to make a lot of new architecture. So of course, they need to be supported by software. And here the point is that it's very important to have hardware, software co-design, so that all the new feature that will be offered by the hardware should be supported by the tooling, so that it will be as transparent as possible for the programmer. But that's indeed, it's very important. And I talk about the new partitioning of memory. So now people don't really care where they are their data. So now it might be new approach where you will, or where the programmer could get hints to the system, so that the compiler or the tool could have more optimization. But yes, and so for me, the key answer to this is that to have more co-design between application, software tool, and hardware on architecture. So perhaps, Craig, if you want to complement.
I think the other thing, so there's a lot of things we can do on the software level, looking at compilers and shared compilers across acceleration, and especially in the open source community. But the other, from a hardware perspective, really the things you have to look at is what are your latency and bandwidth, and how sensitive are you to this. So if we split the elements in the chip, our latency can potentially be higher, and certain workloads are sensitive to that, and certain others aren't. So then adapting architectures so that you can either share memory and, you know, across compute elements, or finding ways to address these latency concerns especially, is the important piece of that.
Thank you. Okay, well, we are running out of questions, and we are also running out of time. So I think we will close for now, unless I have a new question just right now. So I would like to thank you all, Marc, Robert, Tobias, Craig. Thank you for doing this presentation for a second time, because when you signed it for the EuroHPC Summit, you didn't know you'd have to do it twice. So thank you very much. Now it's recorded, so you won't be asked to do it again. And to our audience, well, thank you for being here today. I hope you enjoyed this webinar, and we hope to see you next week for the part 2 of this webinar, which will be dedicated to managing heterogeneity and quantum computing. So thank you, everyone. Thank you for being here today, and talk to you next week.
Bye.